Good morning, everyone. If you wanted to stand up and stretch, it's okay. Like you, I've been sitting here for the last 2 hours, and so I have two jobs today. One is to close the morning session and get us to lunch, which I think we will do. And the second is to make a couple points on the need for measurements and measurement-based models. Okay, so again, thank you for inviting me. I am delighted to be here. And okay, so for those of you who are not familiar with the Communications Technology Laboratory at NIST, we are moving very fast here. Thanks. Okay, so we basically, as part of an NMI, we specialize in high-quality measurements in instrumentation to enable technology innovation, but also accelerate the development of standards, as standards is in our name. So our programs run the gamut from in the Communications Technology Laboratory, from chip-scale devices all the way to wide deployments like Rydberg atom, quantum communication sensing, and 5G and 6G. So let me explain a little bit what I mean by more with less. I think we're here this morning and we've been reading about all the wonderful things that 6G is going to enable. We want better performance, better reliability, better coverage. We want to do so much more with 6G. And we saw wonderful videos. Disclaimer, no videos. You're looking at the graphics design department. So all of these slides are basically my own. So I apologize in advance for maybe they're not that trendy. Anyway, so let's get back. So we need to do a lot more. And with 6G, we think we can do even better and more. However, we're starting to hit that limit where we are seeing that spectrum is not unlimited, and we have to contend, and it's a very crowded space and allocation. We're also hitting the limit in terms of energy and energy consumption, as our consumption of energy, especially with AI and other computation-intensive applications, we're basically consuming more than we're producing at some point. So I want to think, maybe because I'm coming from a National Metrology Institute, that there is a need for measurements and measurement-based models in order to help us better design and design a more reliable, more resilient 6G. So this is basically the message for you all today, is for the need for measurements and measurement-based models, and we need them in all of these different areas. And to basically do better optimizations, and to enable standardization, obviously, and to accelerate the use of AI ML. One other thing that we all learned is basically AI is wonderful. However, we still need to have a network and a foundation in order to run AI. So let me do this. We're going to go through sort of the drivers, the needs, and then some of the constraints, and then we'll talk about the measurements, what we desire in terms of curated data sets. That's the need that is, I think, very significant today as we're using more of AI and ML. And I'll provide an example for some of our programs supporting the development of ISAC, the sensing and communication that is seen as a feature for 6G. That's very good. I think that's another benefit for coming a third speaker, is that basically they all make my life easier in terms of I don't have to convince you that you're going to have wonderful things with 6G going forward. As it is today, we're seeing it's a lot more than communicating using a radio device, right? So advanced and wireless communications touches all aspects of our lives with enabling applications that we all benefit and use, from life sciences to healthcare to transportation, mobility, and the like. So for all of these things, we're looking at high bandwidth, ubiquitous coverage, and an intelligent, quote unquote, or automated or wireless infrastructure. So let's see how we're doing on all of these properties. So when we look at high bandwidth, these are forecasted These are forecast reports that I found. And it seemed like, for mobile data, when we're talking about audio, social networking, web browsing, all of these things are sort of increasing, but not as much. What is really the biggest share in the mobile data is really video. And just to wrap our head around some numbers here, because we all like numbers, in a 4K video stream is about 15 megabit per second. If you're looking at a hologram, double that. If you're looking at an immersive application, all the way to 1 gigabit per second. So that's sort of where things are growing, at least that's one forecast. Another thing to keep in mind is that the mobile data growth rate is falling, has been falling for the last decade by 6% per year. Interesting. So where is the data coming from? Is it really audio, voice? It really is about the connected devices, these sensors that are generating the data. We're sitting at 30 billion IoT devices connected today, and that is growing. So we're seeing a shift in basically, we're moving from a user-centric, where the user generates the data and consumes the data, to more of a machine generating data and machine consuming data. And that's kind of fits within the models that have been described before. So that's basically looking at a sensor data trend, where there's sensors everywhere. And we spoke about the need for coverage, ubiquitous coverage. And how are we doing on the coverage map? So this is the world population coverage by technology. We see about 65% of the world population is covered by 6G. 5G, I'm sorry, not yet. For 6G, we'll have to wait a little bit more, although the hype is there. But in 2025, 65% is covered by 5G. About 95% is covered by some G. So we're doing pretty good, right? However, the coverage story is very, very different. The reality is very different if you're living in a dense urban environment or if you're living in a rural environment. If you're the indoor coverage versus the outdoor coverage, also those are very different realities. So in order to, so there's still basically, in other words, there's still work to be done in terms of doing coverage, in terms of achieving coverage. I think we had a similar chart, basically, but basically where this intelligence is going to come from, right? It's basically we have sensor data. If we're equipping every communication device with a sensor, we're able to harness a lot of data. We're able to process this data to tell us about the environment, how what we're doing, what we need to do, and adapt the network, the system, to the environment. And that's where sort of the smart intelligence is going to come from, right? So as we acquire more environment information, we're able to turn the wireless signals and use them in order to understand more things. And we're also going to be able to support a lot of the sensing applications that we saw are very useful in so many different domains. Wonderful. So let's talk a little bit about the constraints that I alluded to and that were sort of on our mind. So obviously, when we're talking wireless, we're talking about spectrum, right? And a spectrum need for an application typically is proportional to the bit rate. As we have more bit rates, we need more spectrum. So just a figure of just to understand things a little bit, a 15 megabit video connection requires about a fraction of gigahertz, basically 30 maybe megahertz. If we go to all the way metaverse and immersive application, we're looking at maybe a couple gigahertz. When we're looking at the sensing, we said that sensing was important. So the figure there that's important for sensing to tell us about if we're able to distinguish between two objects is called the sensing resolution. And the spectrum need there is inversely proportional to that sensing resolution. For example, for an indoor application requiring centimeter kind of resolution, we need tens of gigahertz. If we're looking at an outdoor, maybe a sub-meter resolution, sensing resolution may be a fraction of a gigahertz. So as you see from this, it's a very different need depending on the application and what we're trying to do in terms of the spectrum. And then we come and then we say, okay, where do we find this spectrum? I'll spare you the very busy, colorful spectrum allocation map. At least I think every country has one. In the US, we have one, and it's very busy. I'm just going to want to highlight the spectrum bands that were identified in the last World Radio Conference in 23 for 6G. So those are in the mid-band, the lower and upper mid-band. And those bands are known for sort of good propagation properties if you want to cover a wide area. So obviously, if you want to do things that are a little bit more need more spectrum, we're going to have to go higher in the frequencies, maybe all the way to the sub-terahertz. So this is sort of the reality of the spectrum, right? Of course, we're going to do more with sharing, doing more things more efficiently, but this is what we have to keep in mind because it is not an infinite resource. Something else that has been on a lot of people's minds recently, it's about the energy and the energy consumption, right? We're building nuclear reactors. We're looking at how do we increase the electricity production. And as it is apparently it's growing every about 2% per year. Not going to be able to keep up with the ICT demand that is doubling every 3 years, right? So going from 4G to 5G, we were able to do a lot of things, right? We added throughput about 16 times, we added bandwidth about 5 times, but we also added energy consumption about 4 times, I read. And we shifted the consumption from the RAN to the data center, where we're crunching all the numbers and running a lot of the algorithms. So therefore, if I wanted to project into 6G, and without doing anything different, I will quadruple the energy consumption. It's obviously that's not something we can keep up with. So that's something that we need to pay attention to, where we need better energy models, better measurements in order to assess the energy consumption. The last papers that I'm looking at that talk about this are basically 10, 15 years old. So it's obvious that a lot of things have happened since and that we need to pay attention to. Okay. So let's talk about intelligence. I think we all sort of drank the Kool-Aid. We're all on board. The AI train has left the station, and we think we can do so much. And people have been doing things in wireless communications. It was called neural net, and it was called many things. If you were in this field, you've sort of been doing things for some time. But regardless, so the latest trend here is to use these LLMs or LMMs, multi-modal, because it's not just language, it's not just text. We're dealing with different types of inputs and different tasks as well, is to take pre-trained models, whether it's GPT-4, it's Gemini, Llama, whatever you like, and they're trained on trillions of tokens and have billions of parameters. So you don't have to do that because it's been done, but you just have to use it for your own specific domain. And how do you do that? You fine-tune it. And how do you fine-tune it? You basically have to use curated, labeled data sets that really describe what you want to do. So then you can use that to doing various signal processing functions, data analytics. We saw in the previous talks, many examples for that. And there again, as you have the output, you still have to validate it. And how do you validate it? You still have to have benchmark data to validate it against. So if everything I said basically today is to motivate the need for better measurements, better models, measurement-based models, it's having to deal and having to use this AI in telecom. Nothing illustrates it better than the need for measurements and curated data sets than this particular, how we're going to use this. So that is basically the motivation, I think, that sort of tells us how important that is. So what is the state of the art today? Over 100 papers on LLMs for the last 5 years. They all talk about, they have one thing in common, or maybe probably more than one. But one thing that I'll mention is that the need for curated data sets. If they're from different groups, they never use the same data and they never shared their data, right? And obviously, if we as a community have to go forward, have to advance and use this to our advantage, we have to do better. We have to come together to put this out there. So where's the state of the art today in terms of curated data sets? Lack of standards, no annotation labeling issues. Obviously, the telecom operators have access to the data, but they can't release it for privacy concerns. It's not one type of data, right? We're not just talking about text. We're talking about different types of data, whether it's lower layer IQ samples, or it is routing data, or it is or it's user behavior, user mobility. So as you see, it's multifaceted, but very high dimensionality data. And then of course, it covers different areas, different use cases. So it is not that simple. So this is a desired wish list, and it's not exhaustive, but these are some of the things that people think about. On the right, people often say, we want an MNIST for wireless. Well, I'll tell you what an MNIST is. It was published by NIST in 1990, 35 years ago, and it was 60,000 images to be able to, it's basically characters, handwritten characters between 0 and 9. And they had 60,000 images to train the algorithm, and 10,000 images to test it, right? So since that time, we're far, far, far from that simple world, right? Where you just needed 60,000 images to train an algorithm. And as we see, it's a very complex system that we are dealing with. So what do we want? Basically, we want high fidelity, high realism, right? We can even generate synthetic data, but they have to be real, and they have to be close to reality, to what the real systems are. Obviously, we spoke about multi-modal, multi-layered. They have to have ground truth, spatio-temporal, so that we can understand where things were collected. It has to be labeled, annotated. It has to have multi-diverse, different coverage areas. It has to be able to be reproducible and traceable to something. And then obviously we want standards, formats, scale, et cetera. So as you see, this is a long wish list of what we need as a community. I'm not saying that data sets don't exist today. In fact, a lot of data exists today. We have been telling researchers to publish their data, and they've been doing just that. But the problem is we don't have curated data sets that we all can be using and using in order to benchmark our results. Okay, so NIST has been in this business of curated data sets. We have been looking at a very niche area, which is RF propagation measurements. And about 10 years ago, we founded this Next-G Channel Model Alliance, which is really about creating a place for consumers and producers of RF propagation measurements to share their data. And so nextg.nist.gov, this is where you sign up. It's where the repository of the data is. It allows people to browse for different data sets of interest. And based on coverage, based on indoor, outdoor, different scenarios, and then use that. So we've been having some success. In the last, I'd say, year or so, we've seen a lot more people interested in this, given the interest in AI and ML. And then we take great care into describing the data, producing this metadata, the parameters, the description of the instruments, with which the data was collected, et cetera. So now I'm going to pivot into the giving you an example of the integrated sensing and communication program that we have at NIST that actually supports the development of ISAC for 6G. And again, to give you an example of where good measurements and models are helpful to develop 6G. So we'll start from the measurement, the instrumentation, then the abstractions, the model abstractions, and then talk about the standard development and the dataset dissemination, which I just described with the NextG Channel Model Alliance. So starting with the instrument, what we have is, this is our 5th generation channel sounder for RF propagation measurements that we've equipped with LiDAR and camera. So all of these 3 signals, the RF, the LiDAR, and the camera, are synchronized in time. And what you're getting is you're getting the images of where the data is being collected, and you're giving a LiDAR map, which is very useful for us when we did this in order to understand better the environment so that we can automate the processing of the RF, post-processing of the RF data. It's also been very useful for people interested in building these digital replicas. I'm not going to say digital twin, because to me it feels it's a lot more than just having a digital representation of the environment. We still have to have a feedback loop in order to do something about what we're collecting. But nevertheless, people have been using this data to build these replicas, and also to run AI, ML, do AI-based channel modeling, etc. And because it's sensing, and we're dealing with, we're going to equip the communication system with sensing, while we do have good propagation models for communications, we don't have them for sensing. So we have to extend the current propagation models in order to do sensing. And one of those things we need to do is understand target sensing propagation with respect to different targets, different objects, different physical objects. So we've been doing measurements for humans in order to do gesture recognition, walking, breathing, vital signs, vehicles, robotic arms, drones. And from the different measurement campaigns, we basically can build different models. And there's not only one model that people are interested in. Depending on what they're doing, they could be looking at more complex model or simpler model. If we're looking at a drone detection outdoors, we probably can have a single ray, very simple model that could be used. Or if we have a gesture recognition, a sports kind of monitoring, then we need something a little bit more detailed. So we have used these to contribute to different standard development bodies. Starting in 802.11, the BF extension is for sensing. And we worked with the committee in order to extend the channel modeling in order to include the measurement-based. Also, with the Next Generation Alliance, the ADIS Next NGA, they've had a group that has been looking at measurements and models for ISAC. So we used our measurements in order and worked with our partners in order to develop these channel measurements and models. And then this past year, where the actual 6G standard development has started, they always start with channel modeling. And this is where our measurements have fed into this in order to extend the 38.901 specifications for channel propagation. So as you see from the instrument, the measurement, the models, then the standard, it's sort of a nice loop there. We have also done something which is to enhance the measurement-based modeling, so that we have created a path between the measurements and the models that are developed, and worked one-on-one with many vendors. Some of them are here today, in order to enhance their models with the measurements. We've also done is updated or improved on tools used by hopefully a lot of you and are available in the public domain. And those, to capture the measurement into these models. So One of them is the channel realization, from the measurements to realizing a channel to actually developing the physical layer and also the system level. In blue, these are things that are models that are NIST developed. In green, it was a community effort that we helped or improved other models that people have done. So basically, this gives you an example where you define the environment, the target in this case, because we need communication and sensing. So there's an environment information, but also target information. Is it a human? Is it a car? Is it an object? And then we basically feed that into the channel realization software, and then it spits out the sort of the model. The MPC component and the properties. And then here we have another example of our Wi-Fi sensing, which is it's just a physical layer model that's also available on GitHub for Wi-Fi. More recently, we have looked at how do we use 5G new radio for sensing. This is on the way to 6G, right? 6G standards has just started. People have talked about items, study items, but before they do that, they want to understand how can you do it with the 5G with the 5G signals. So that's sort of brand new, where we actually we'll release this module built on the MATLAB toolbox, 5G MATLAB toolbox, and we can ask questions as to what is the sensing, what is the misdetection, what is the position error, etc. So when it comes to sensing and communications, so there are many performance trade-offs that one could ask. And one of them is, so they're sort of more system level, right? At the system level, how do we design this sensing to take advantage of the signals that are there, or do we actually want to go and use communication just for sensing, right? So this is the active sensing versus the passive sensing, where you're actually using the communication signal and you're trying to harness information about the environment. So we've done a number of studies on this active versus passive with Wi-Fi and with 3GPP. So that is something to still to be discussed. There are many open questions on the sensing and communication, how this is going to be integrated into the current standards and what extensions are needed. And many system parameters are going to come into play, and what's going to, many things are going to be affecting the performance, the bandwidth, the beam width, the transmit power, obviously. The target RCS, the larger the object is, the more we're going to be able to detect it, things like that. A lot of details and a lot of good measurements that need to go into this in order to really design the system. I think, so I spoke about the sort of the measurements on nextg.nist.gov. This is more for propagation. I don't claim that I'm solving the entire measurement problem. However, it's a small step into that, and as a community, hopefully we could do more. There are perhaps internship opportunities, so if you're interested, please see me after this. And yeah, so I